Hey, Russell, what you reading?
The Bible, 1 Kings 7:23.
What's it say?
And he made a molten sea, 10 cubits from one brim to the other. It was round all about, and his height was 5 cubits, and a line of 30 cubits did compass it round about.
Wait a minute. That suggests that the value of pi is 30 over 10, or exactly 3. Most books tell us it's more like 3.14159. We'd better investigate. Okay, we're going to be investigating the value of pi. To do this, we're going to start by talking about triangles, and then circles, then pyramids, and then spheres, and go on from that to the actual value of pi itself. Now we're going to be focusing on a particular kind of triangle called an isosceles triangle. I didn't write isosceles up here because I don't know how to spell it. But what makes an isosceles triangle special is 2 of the 3 sides must have the same length. The third side could be relatively long, like with this isosceles triangle here, or it could be relatively skinny, like this isosceles triangle here. Now the formula for the area of a triangle is 1/2 times the base times the height. Here's why that formula works. Our tall, skinny isosceles triangle has been drawn inside a rectangle, and you can see that the triangle itself occupies precisely half the area of the rectangle that it's in. That's where the 1/2 comes from. Hey Russell, what can you tell me about that circle in front of you?
Well, the 4 triangles inside are taking up most of the space except for the black parts.
Okay. What can you tell me about the black parts?
Those are the parts that are not taken up by the triangles.
Okay. Now here's another triangle, and what can you tell me about it?
This circle has even more triangles than the last one, and less black space.
Okay. Now, the viewers need to see it from their own perspective. So could you do them the favor of turning it around?
Yeah.
Much better. Okay, here's circle number 3. What differences do you see from circle number 2?
There are yet even more triangles and yet even less black space, and there seems to be a star-like pattern directly in the middle.
Oh gee, I wonder where that star-like pattern came from. Maybe it's because the lines that I drew in the circle weren't infinitely skinny like theoretical lines are. Anyway, in this case, the triangles seem to be occupying almost all of the circle, just like you said. Okay, we're going to review the parts of the circle now. We're going to use the letter C to represent the circumference of the circle, which is the distance around the circle. And the circumference is equal to the value of pi times the diameter, where the diameter is the distance across the circle. By definition, pi is the value that you multiply the diameter by to get the circumference. And the diameter is equal to 2 times the radius of the circle, because the radius goes just halfway across from the middle to the circle itself, and the diameter is twice that long. So we have C, the circumference, is equal to pi times 2r. Okay, we just looked at 3 circles. One of them had 4 triangles inside of it, the second had 8 triangles, and the third had 16 triangles. Now, I want you to imagine a circle that doesn't have 16 triangles drawn inside of it, but has billions and billions of tiny, tiny, skinny isosceles triangles. Now, 16 triangles were almost enough to take up the whole area of the circle, And if you've got billions and billions of triangles instead of 16, you're really going to be getting close to occupying the entire area of the circle. Now, each one of these billions and billions of isosceles triangles is going to have an area equals 1/2 times the base times the height. I'll just rewrite that formula again. 1/2 times the base times the height. Each one of these bajillions of triangles will have this area, and let's rewrite this a little bit. We'll keep the 1/2, and the base of each triangle is going to be approximately the circumference, C, divided by n, where n is a really, really huge number. It represents each of these bajillions of really skinny triangles. So that's the base. And then the height of each one of these triangles will be very close to the radius of the circle. Now, this is the area of each one of these triangles, and to get the full area of the circle, we're going to have to take that and multiply it by the number of triangles, which is n. So we've got the area of the triangle, or the circle, is very close to n times 1/2 times circumference over n times r. Now we can start to simplify. These n's will cancel, so we're going to have 1/2 times the circumference. But remember, the circumference is pi times 2r times, so we've got pi times 2r times r. And now this 2 and this 1/2 will cancel. So this is going to equal pi times r equals pi r squared. You've seen this formula in books. Now maybe you've got a better feel for why it works. Hey, Russell.
Hey. Better check all 3 dimensions, Dad.
Okay. The next step in our study of pi is to consider maybe the most difficult question that we're going to face. What is the surface area of a sphere? Now, the textbooks tell us that the surface area of a sphere equals 4 pi r squared. But we don't want to just take that on faith. We want to investigate whether that's really true. And to help us with our investigation, we have this stuff that I've put together over here. What we have is a blue sphere, and the blue sphere is surrounded by paper. Now let's look at this paper. There's something special about it. First, the height of the paper is equal to the height of the sphere, and the height of the sphere is equal to 2 times the radius. It's equal to 2r. And if we were to unwrap this paper, the length of the paper is going to equal the circumference of the sphere. And the circumference is equal to 2 pi r. And when we do the multiplication, we get 4 pi r squared. So here's the question. When we unwrap this paper, will the rectangle that we get have the same area as the surface area of the sphere? That's what we're going to investigate now.
So here's the question. Does the area of the brown paper equal the surface area of the sphere?
Okay, here's the next step. we have our sphere and we have our rectangle next to it, and we're discussing whether the area of the rectangle equals the surface area of the sphere. Now, I am wanting you to imagine that we're going to take the sphere and the rectangle and draw stripes across both of them. So it looks kind of like this. So near the equator of the sphere, you'll have a red stripe like this, and you'll have a corresponding red stripe going across the rectangle. Now the height of the stripe here will equal the height of the stripe here. And remember, this really is a sphere. It's not just a circle. So the length of the stripe here actually equals the circumference of the sphere, which is also the width of the rectangle. So this stripe on the sphere has the same area as the corresponding stripe on the rectangle. But does this stripe that's closer to the North Pole of the sphere have the same area as the corresponding stripe on the rectangle? This is kind of tricky to discuss, but let's take a shot at it. At first glance, you would think that this stripe is smaller than this stripe, and therefore smaller than this stripe, because it's not so far from left to right. At the equator, you have a greater length from left to right. So if this stripe isn't as long, how can it have the same area as the stripe at the sphere's equator? The explanation lies in the concept of the slant height. Now let's imagine that you're a painter, and your job is to paint these two stripes on the surface of the sphere. The first stripe that you'll paint will be close to the equator of the sphere, and the red area represents the paint that you've got to put down on the sphere to do your job. Later, you're going to be painting this stripe closer to the North Pole of the sphere, so to speak. And at first it looks like the height here is the same as the height down close to the equator. But that's really kind of an illusion. The real height of the stripe that you have to paint closer to the equator is represented by the length along the sphere, the length right here. And you'll see that this slope height right here is much longer than the corresponding slope height close to the equator of the sphere. So as the width of the stripe gets less and less, the slope height gets greater and greater. And if the rate of increase in the slope height matches the rate of shrinkage in the length of the stripe, then our hypothesis about 4 pi r squared may still be true. Now this may help a little. I've drawn two stripes on this sphere that are like the stripes we've been talking about. The first stripe here is drawn along the sphere's equator, and the second one is drawn closer to the sphere's north pole. Obviously, this stripe by the equator is longer. It has a longer circle to go around than the higher stripe closer to the North Pole. On the other hand, the width of this stripe is best seen if you look straight down on it. And the width of the other stripe is also best seen if you look straight down on it. And you can see this stripe may not be as far around, but it is wider. So it's at least possible that the area here is equal to the area here. That's what we're going to check. Now imagine that this partial circle we have here is the outline of a sphere, and this point, we'll call it point A, is the center of the sphere. Now I'll just pick a random point along the circle, and we'll connect it to the center. So we've drawn a radius of the circle. And we'll call this point B. Now we're going to draw the tangent to point B. It's a line that will touch the circle at only one point. That point will be point B. And we'll just draw this tangent down to what we'll call the equator. And where they intersect, we call that point C. So now points A, B, and C form a triangle, and since BC is a tangent of the circle, that always means that it's a right triangle. Next, we're going to draw a line straight down from B to the equator to form two more right triangles. And whenever we take a right triangle and cut it into two smaller right triangles, the two smaller right triangles always have the same shape. Now we're going to call this point D right here. And we have two triangles that we'll be discussing with the same shape. One of them is ABD. Let me just outline that in red. Come on, red. And the other right triangle with the same shape is BCD. Now, one last point we're going to label. Point E. Here where the circle intersects the equator. So, ABD is a right triangle, and the hypotenuse is AB. BCD is a right triangle, and the hypotenuse is BC. So these are corresponding sides. Now in this right triangle, the second longest side is AD, and in this right triangle, the second longest side is BD. Now, AB is a radius of the circle, and AE is also a radius of the circle. So we're going to substitute AE in for AB. So now we have AE over AD equals BC over BD. And simple algebra allows us to rewrite this to say this. AD over AE times BC over BD is equal to 1. Here's why this is important. The ratio of AD to AE, shows how much the stripe going around the sphere shrinks when we go from the equator up to point B. And the ratio of BC to BD is the ratio of the slope height to the straightforward height. That shows how much wider the stripe has grown when we've gone higher up on the sphere. The amount by which the length of the stripe shrinks precisely equals or corresponds to the amount by which the slope height of the stripe gets bigger. And that's why over here, the area of this stripe equals the area of this stripe. That we have demonstrated. So, here's what we just demonstrated. When you look at this sphere and these two stripes on the sphere, the green stripe, which is higher up, closer to the North Pole, so to speak, is narrower than the red stripe closer to the equator, but because of the slope of the sphere, the green stripe is also, in a sense, taller than the red stripe. And the amount that it's taller perfectly compensates for the amount that it's not as long, so the area of this part of the sphere equals the area of this red part of the sphere. In fact, all of these stripes on the sphere have equal areas. So the surface area here equals the surface area here, which also equals the area on the rectangle over here, because it's the same height as here, and it's the same length. And all of the stripes on the rectangle have equal areas. What I'm saying is each stripe covering part of the sphere has the same area as the corresponding stripe on the rectangle. So the surface area of the sphere equals the area of the rectangle. Since the area of the rectangle is 4 pi r squared, that is also the surface area of the sphere. And that is what we were setting out to demonstrate.
Dad, I have a question.
What's that?
What if you divide the length of the rectangle by the height of the rectangle?
Well, 2 pi r divided by 2r gives you pi.
I think I have a way to measure pi.
Okay?
Let's see how many times the width goes into the length. That's 1. That's 2. That's 3. And there's a little more.
Wait a minute. That little bit more wasn't in the Bible. Maybe we need to take a more sophisticated approach. Okay, our more sophisticated approach to examining pi is going to start with a review of a triangle. Remember we said that the area of a triangle equals 1/2 times the base times the height. Now we're going to move from a discussion of the triangle to the discussion of something that looks a lot like a triangle, a pyramid. A pyramid has 4 sides here that all have the shape of a triangle, but its base isn't simply a line. Its base has 2 sides, and its base has area. Now, when we look in a textbook, we can see this formula. A pyramid has a volume equals 1/3 times the base times the height. Now that's very similar to the formula for the area of a triangle, but there's this one very noticeable difference. The multiplier for the area of a triangle is 1/2. And the multiplier for the volume of a pyramid is 1/3. Now maybe that's simply because a triangle has 2 dimensions and a pyramid has 3 dimensions. But we're going to look into it a little bit more deeply than that. Now here's one thing you'll notice about a triangle. When you go halfway up from the bottom to the top, the base halfway up is exactly half what it was at the bottom. But when you take a pyramid and you go halfway up from the very bottom to the very top, something different's going on. Here is what's happening. let's just draw the base at the very bottom. Not a precise square, but I'm just trying to give you the idea here. And now, when you draw the base halfway from the bottom to the top, the cross section halfway up isn't half of what it was at the bottom, it's closer to 1/4. Okay, continuing with a discussion of the volume of a pyramid. I should mention when I look at the drawing here that this looks like it's a little more than 1/4. I'm just trying to give you the idea. I'm not always the best artist when it comes to this. Now I'm going to try to relate this idea to the idea shown by this curve here. Now I've laid the pyramid out next to this curve. This curve is a graph of the relationship y equals x squared from x being 0 to x being 1. And here's what the graph has in common with a pyramid. At the tip top of the pyramid, when you're 0% of the way down from the top to the bottom, the cross section has an area of 0. And when you're at the very bottom, at the very actual base of the pyramid, the base is 100% of the base because it is the base. That's why we have one graph here. And when you're halfway between the two, then the area of the base is 25%, 1/4 of what it was at the very bottom. And so this point corresponds to 100% of the base, this point corresponds to 25% of the base, and this point corresponds to 0% of the base. And it happens that the area under the curve here is precisely 1/3 the overall area of the rectangle shown in the graph. I'm just hoping that'll give you a sense of where this 1/3 multiplier in the volume formula came from. Okay, we have one more argument that it's plausible that the formula for the volume of a pyramid is 1/3 times the base times the height. What we have here looks like a regular cube, but within the cube there lie 6 pyramids. Every cube can be divided into 6 pyramids with equal shapes. And each pyramid has as its base one of the 6 faces of the cube. And the height of each pyramid is going to be 1/2 of the length of the side of the cube. Okay, now we're going to think about this algebraically. So each one of these cubes, or I should say each one of these pyramids, has as its base s squared, the length of the side of the cube squared. And the height is going to be the side divided by 2, because each pyramid kind of goes halfway through the cube. And then we're going to multiply this by the mysterious multiplier m. And our task now is to figure out what m is. So for the whole cube, we've got 6 of these pyramids, so we take the volume of each pyramid and we multiply it by 6. And we get this value here. 6 times the value s squared times s over 2 times the mystery value m. And also, the volume of the whole cube is equal to s cubed. That's the standard formula for the volume of a cube. Do a little algebraic manipulation. We get 3s cubed times m equals s cubed. This implies that m equals what we get when we take s cubed and divide it by 3s cubed. And the s cubed terms cancel, and we get 1/3, which is the value we were looking for. So our plausibility is established. We've got a basis for accepting that the volume of a pyramid is 1/3 times the base times the height. Hey Russell, let's review. What can you tell me about that circle in front of you?
This circle has the most triangles and the least amount of black space.
Okay, which seems to suggest that when you put together lots and lots of really skinny isosceles triangles, you can get a good approximation of a circle. Now, extending this, what can you say about the other stuff on the table?
You can approximate a sphere with lots and lots of really skinny pyramids.
Well, maybe. Let's pursue this. Okay, it kind of works like this. Now, this pyramid isn't as skinny as it might be, but this might give you the idea. Here we've got a sphere, or a ball that's pretty close to being a sphere, and it's got some shapes drawn on the surface, and some of these shapes are similar to the base of the pyramid. So just imagine that this ball, this sphere, is made up of lots and lots of pyramids like this, and the base of the pyramids form the surface of the sphere, and the tips of the pyramids, this part, all come together right at the center of the sphere. So, putting a few things together, here's what we have. The formula for the volume of a pyramid is 1/3 times the area of the base of the pyramid times the height of the pyramid. Now, if we're going to make up a sphere from a humongous number of really, really skinny pyramids, the whole volume of the sphere is going to be equal to the volume of each individual pyramid times the number of pyramids. And let's say that the number of pyramids is equal to n. And remember, n is a huge number, billions and billions in theory. So let's pursue this a little bit more. This will equal n, the number of pyramids, times 1/3 times, now here's the tricky part. What's the area of the base of each one of these pyramids? Well, it's going to equal the entire surface area of the sphere divided by the number of pyramids. And the surface area is equal to 4 pi r squared. We're going to take that entire surface area and divide it by the number of tiny pyramids, which is n. And the height of each one of these pyramids is going to be the distance from the center of the sphere to the surface of the sphere, and that is simply equal to the radius of the sphere, which is r. Now, the n here and the n here cancel, so we can simplify to this. It's going to equal to 4/3 times pi times r squared times r. Or, to put it all together, 4/3 pi r cubed. We have just derived the formula for the volume of a sphere.
Okay, so we have the formula for the volume of a sphere, but what good is that? Our goal is to find the value of pi.
Hey, isn't it obvious? Okay, Here we have 3 balls and we have a cube. And you'll notice that the cube has been molded very, very precisely to have dimensions that parallel those of the sphere. The length of each side of the cube is 2 times the radius of the sphere. Okay, here's what we're going to do. Step 1. Now we've filled this cylinder completely full of water, so when we drop in the sphere, the amount of water that spills is going to precisely equal the volume of the cube. Step 1. Gingerly drop the sphere, or the cube, into the cylinder, and the water spills. Okay. Now, what we need to do is measure how much water spilled. And to do that, we will pick this up, put it down, try not to spill anything. And now, we're going to pour the water into our laboratory equipment to measure volume. Laboratory equipment, by the way, purchased at Axeman Surplus. Great place for laboratory equipment. And I'm going to look at the measure, and in terms of cubic centimeters, it's 200 cubic centimeters. Take my word for it if you can't quite make it out. Okay, so what we just found out is that the cube, which has each side equal to 2 times the radius, so it has a volume equal to 2 times the radius, the quantity cubed, which equals 8r cubed equals 200 cc's, or 200 cubic centimeters. Okay, let's proceed with part 2 of our experiment here. The 3 balls, gingerly put into the cylinder. Now let's carefully remove this. Oh, just a drop or two, just a little experimental error, not a problem. And I believe that's about 300 cubic centimeters. Let's write that down. Now each ball has a volume. Let's see, what did we say the formula is for the volume of a sphere? 4/3 pi r cubed would be the volume of each of the spheres. But we have a total of 3 spheres. So this was equal to 300 cubic centimeters. And let's just proceed with this a little bit. This 3 and this 3 cancel. So we have 4 pi r cubed equals 300 centimeters, or cubic centimeters. And if we double each side of this equation, we will have 8 pi r cubed equals 600 cubic centimeters. So, putting together two pieces of information, we have 8 pi r cubed equaled 600 cubic centimeters, and we had simply 8 r cubed equals 200 cubic centimeters. So, we should be able to maintain an equality if we divide the 8r cubed by, or 8 pi r cubed by 8r cubed, and divide the 600 cubic centimeters by a value equal to the 8r cubed, which is 200 cubic centimeters. Doing this, on the left side, 8 pi r cubed divided by 8r cubed is simply equal to pi. And on the other side, 600 cubic centimeters divided by 200 cubic centimeters equals 3. Hey, hallelujah! We've confirmed the Bible. Pi is equal to 3. What do you know?
Wait a minute, Dad. There's still a little water left in here. You gotta be careful when you're studying the Bible. It looks like pi equals 3 plus a little more.
Now, actually, you've probably guessed that the equipment you can buy at Axeman Surplus isn't exactly what you'd call scientific caliber. And the 3 balls I was juggling may not have been perfect spheres, and the cube that I used for measuring may not have been a perfect cube. And even if it was, it probably had sides that were not exactly 2r. So we've been dealing with approximations. Actually, what we should say is 8r cubed in this case was approximately 600 cubic centimeters, and 8r cubed was approximately 200 cubic centimeters. And pi was very approximately equal to 3, or if you wanted to be more precise, 3.14159. But we need to leave this as a squiggly thing rather than an equal sign, because even 3.14159 is simply an approximation.
But the Bible says that that round thing is 30 cubits around and 10 cubits across. That implies that pi equals 3.
Well, it would seem to, but you know, we all round things off in our day-to-day life. We have to, or else we'd go crazy. Maybe it's something like this. These days we have a concept called the decameter, which equals 10 meters. Maybe back then they had a concept that we've forgotten about that was something like the decacubit, which would be 10 cubits. And maybe when they wrote that part of the Bible, they just rounded everything off to the nearest decacubit.
Does that mean everything in the Bible is rounded off to the nearest decacubit?
Well, that's a tough question. It's an excellent question, but it is beyond the scope of this video.